Okay, so now we're going to talk about combustion reactions, and we're going to do two things in once. We're going to talk about the type of reaction and how to determine just by sight, by looking at it on paper, that it is a combustion reaction. And we're also going to talk about balancing those, because balancing combustion reactions can be a little bit tricky, but I'm going to give you a super helpful hint and some steps, that way you have no problem balancing combustion reactions. So first and foremost, you want to look at these three reactions, or look at the two at the top. What do you notice is the same about both of those reactions? It starts out with what we call in chemistry a hydrocarbon. A hydrocarbon is an organic compound. They're basically fuels. Okay, they're basically alcohols. And I'm not talking about the alcohols that I'm talking about the ones that we use as fuel. Gasoline, ethanol, methanol, any type of clean, gasoline's not really one, it has ethanol in it. But a clean burning fuel are considered organic compounds. They're a combination of just carbon and hydrogen, which is why they're called a hydrocarbon. So you're going to see a hydrocarbon in the front, okay? But that's not the telltale sign. The telltale sign is this right here. In order to burn something, a combustion reaction is one in which you're exploding or burning anything. I don't care if it's hair, paper, a book. Anything that you're burning is considered a combustion reaction. In order for anything to burn, what must be present? If there's no oxygen present, then the flames can't get enough oxygen, obviously, to breathe. So if there's no oxygen, there will be no flames. There'll be no burn. It will go out. So anytime you're combining anything with oxygen on paper, you're saying, hey, I'm setting this on fire, and these are going to be my two products, right? Anytime you set an organic compound on fire, you only get carbon dioxide and steam or water vapor, which is still H2O. So this becomes your telltale sign for combustion, okay? And let me explain to you why it cannot be, even though it might look like one of the other types of reactions, a single or a double displacement. Let me tell you why it can't be. The rule for synthesis reactions is that you cannot have plus signs on the right. Because there's a plus sign here, it cannot be synthesis. Because there's a plus sign on the left, it cannot be a decomposition reaction. So now let's talk about single and double. In order for it to be a single replacement reaction, you have to have a single element on both sides of the arrow. Here we have oxygen, which is considered a single element. But are there any single elements here? No, it can't be single. For the same reason, it can't be double. In a double replacement reaction, you have to have 4 compounds. 2 compounds on each side. You cannot have anything that's alone or a single. So because this oxygen is there again, it can't be double. So once you go through all 4, it can't be synthesis, it can't be decomp, it can't be single, it can't be double. You're just going to look for this. O2, CO2, H2O. And you'll have several questions on your end of course exam where they will give you something like this. And this side will be blank, and they'll ask you to finish out the equation. What are the possible products in a combustion reaction? Or what are the possible products in the following reaction? And you just have to memorize a combustion reaction. If it's an organic compound, a hydrocarbon, burning in oxygen, then CO2 and H2O are always going to be your products, so that you can finish it out and find the correct multiple choice. So now let's talk about balancing. The hardest thing about balancing combustion reactions is that you end up using pretty big coefficients. Pretty big numbers sometimes have to get used to balance them. And it kind of freaks kids out that all of a sudden you're like, I need 15 of something, I need 20 of something. Those are like pretty large numbers in terms of balancing. So here's my helpful hint. If your carbon is an even number, meaning, look at how many carbons I have here. 2. That's an even number. How many carbons do I have here? 3. That's an odd number. How many carbons do I have here? 2. That's an even number, right? So if your carbon is even, you want to give him a coefficient of 2. That means you want to stick a 2 in the front. So we're going to do this one first. You want to stick a 2 in the front and start from there. And then you have a specific order of balancing. Here's your order. You're going to balance your carbons first. Then you're going to balance your hydrogens, and you're going to save your oxygens for last. There's a reason why. You have oxygen in 2 different spots on the right side. So after you balance carbon, so let's do that right now. 2 times 2, I have 4 carbons on the left. I need 4 carbons on the right. My carbons are good. When you balance oxygen, you're going to mess up your oxygen. When you balance hydrogen, you're going to mess up your oxygen. So it's a good idea to save oxygen for last because you've got oxygens in 2 different spots. So get your carbons, get your hydrogens, and then we'll tackle oxygen last. So now let's look, we did our carbons, let's look at hydrogen. 2 times 2, I need 4 hydrogens. So in order to get 4, right, that doesn't mean I put 4 right here, it means I do the math. What times 2 will give me 4 hydrogens? And that would be 2, right? So now I have 4 carbons, 4 carbons, 4 hydrogens, 4 hydrogens, and now I'm going to look at my oxygens. So I'm going to have to count. 4 times 2 means I have 8 O's right there. But then I also have how many O's right here? 2. Well, there's a plus sign in the middle, so I need to add all my oxygens up. I have 8 right here, plus 2 O's right here, so I have 10 total. So what number can I stick in the front here to give me 10 O's? A 5. 5 times 2 is 10. The last thing that you want to look at when you get done balancing combustion are your coefficients. Make sure that they're not all even numbers. You want to make sure that they're all in the smallest whole number ratio they can be. Because if they're all even numbers, then we might have to reduce. So right here we have a 2, a 5, so they're not all even numbers, a 4, and a 2. So that's the smallest we can get. And you're done. Okay? So let's look at the next 2. This one is not even, right? The carbon is an odd number. So I'm just going to start. I'm not going to put a 2 in the front. He's odd. I'm going to leave him alone, and I'm going to start by balancing. I need 3 carbons on the right. So put a 3 in the front. I'm now going to balance my hydrogens. There are 8 hydrogens on the left. I need to stick a number here that when I multiply will become 8. 4 times 2 becomes 8 hydrogens. So now my hydrogens are good. Let's count my oxygens. They're in 2 different spots. 3 times 2 is 6 plus 4 means I have 10 total oxygens. So I need 10 total oxygens again. 5 times 2 is 10. Right? Let's look at the one at the top. The one at the top has an even number carbon. So if it's even, I need to stick a 2 in the front. 2 times 2 is 4. So I need 4 carbons. 2 times 6 is 12. I need 12 hydrogens. I have 12 on the left. I got to have 12 right here. So what am I going to stick in the front? A 6. 6 times 2 gives me 12 H's. So now this is where you're going to get into some maybe bigger numbers. 4 times 2, I'm counting my oxygens. 4 times 2 means I have 8 right here. Plus 6 means I have 14 total oxygens on the right side. I need 14 on the left. Well, that's an easy fix. What times 2 equals 14? 7. So 7 times 2 equals 14. And then I'm done. So if you pay attention to this, pay attention to your carbon being even, follow these steps, that'll make it so much simpler. And remember that this is your telltale sign, O2, CO2, H2O, in order to recognize that it is a combustion reaction. Okay?